of this talk.
Okay, thank you. I'm going to talk about some work that we're doing on the history, causes and risk of increasing aridity in the southwestern part of the United States. And towards the end of the talk, I will talk about the future, but our approach to this problem has been to look at the history of the hydroclimate of this region over the last millennium. So we will cover the recent history and deeper back history as background to going off into the future. The Dust Bowl drought of the 1930s is the canonical example of drought. This was one of the worst environmental disasters that occurred anywhere in the 20th century. About 250,000 people left the plains areas during the 1930s, mostly for the west, which was a movement of people induced by a natural event that was the greatest ever until Hurricane Katrina came along. Katrina did it in a day or two. The Dust Bowl drought took about a decade to do it. But this has left a very lasting impact on American society. And we now know what the cause of this drought was. And the cause of this drought was this particular pattern of sea surface temperature anomaly. This is the difference in sea surface temperature between the decade of the 1930s and a long-term average over the entire period of observations of sea surface temperature, which begin in 1856. They all come from ship observations. And during the 1930s, what turns out to be critical was that the tropical Pacific Ocean was cooler. This is degrees centigrade, so it's just a fraction of degrees centigrade, that it's what we call a La Nina-like state, but a persistent La Nina-like state that lasted for a decade. There were no El Nino events during the 1930s. And the reason that I can say that this was the cause of the drought, of the Dust Bowl drought, is based on a lot of modeling work which has been done both by our group at Doherty and also by another group at NASA. They're still the only two groups in the world that have done these long integrations of models forced by observed sea surface temperatures. And what we did at Le Mans was we examined the entire period of instrumental observations of sea surface temperatures from ships, which begin in 1856, and we used those observed sea surface temperatures as a surface boundary condition in an atmosphere model and modeled the atmospheric response to those. And then to find out which sea surface temperatures, SSTs, are important, we can then do different runs where we specify the SST in certain ocean basins only, okay? And we did ones where we specified only in the tropical Pacific, others where we specified globally, and others where we specified only in the tropical Atlantic Ocean. And you have to do a large number of these with different initial conditions, and so that they have different sequences of weather in them. When you average over all of them, you get the response which is forced by the boundary condition. So we will look at the ensemble mean response. The picture, the color in the picture is precipitation, and it actually shows you what the global pattern of precipitation that goes with a persistent wet phase over North America. And as a hint to what you see coming later on, it fits, the hydroclimate in this region fits into a global pattern of hydroclimate. When it's wet over North America, it tends to be very wet in the tropical Pacific, which is indicative of warm conditions. So for a drought in North America, you will have reduced precipitation in this La Nina-like conditions. So to look at the time series of precipitation that actually occurred, which is the solid line, this is averaged over the entire southwest. This is from rain gauges, that's what actually occurred. And then the dashed line here is what the model reproduces when it's only forced with the history of sea surface temperatures in the tropical Pacific Ocean. And you can see that it pretty much reproduces most of the ups and downs. This is from 1856 to 2000. Pretty much reproduces most of the ups and downs in precipitation in this area. When we include global SST forcing, we don't exactly get a much better improvement. So it's sort of it's saying that the tropical Pacific sea surface temperatures are the dominant forcing for the hydroclimate history of this region. Okay, so to look at the Dust Bowl drought in particular, from rain gauges, this is what the precipitation reduction was in millimeters per month. Interestingly enough, this amounted to about a 15% reduction in precipitation over normal, but lasting it's almost entirely a decade. But it was only 15%. That's all that was required to produce the devastating effects that it did. This is what we get with the model with ocean temperature forcing absolutely everywhere. And the pattern we get in both observations and models is basically similar. Most of the plains in the southwest is dry, and then around the northern edge and down in southern Mexico, you tend to get the opposite. We'll see this pattern again and again and again as we go on. If we only include the tropical Pacific sea surface temperature forcing, then we get, that's this pattern over here, then we get the basics of this drought. It will turn out, as I'll get to, that the Atlantic has something to say about this drought as well. Okay, now to turning to going a bit further back in time, it turns out that in the mid to late 19th century there were 3 severe droughts. The most severe drought, as a meteorologist would define it, actually occurred from about 1856 to 1865. And then there was another one in the 1870s, which was famous because it went along with all the horrible locust swarms in the 1870s. And then there was another one, in the, go back. There was, okay, and then there was another one in the 1890s. This one actually had a large social impact as well because there was a huge abandonment of the high plains during this drought, and up until this time, the development of the West had been based on the Homestead Act. You just give some farmers some land, and they promised to develop their own water resources, and they meant to do it entirely on their own. When the abandonment during the 1890s drought occurred, it quickly was followed by the Reclamation Act of 1902, when Western congressmen finally recognized that the West was not going to be developed by farmers on their own, and this led, and instead the water would have to be brought to them, and which brought the federal government into power. And you should always remember that the entire western United States is based on a massive application of federal engineering, and their mythology notwithstanding. This is actually, when we get back to the 1890s, there's not an awful lot of rain gauges. There are still some, so we're starting to use tree ring data, which is continuous every year back at least 1,000 years. And this is the tree ring estimate of a quantity that is very closely related to soil moisture for the 1890s. This is what the model gets, the actual soil moisture in the model, when it's only forced with tropical Pacific sea surface temperatures. So again, this drought is being reproduced as a consequence of tropical Pacific forcing, and as you'd expect, the tropical Pacific was cold during the 1890s. And this was true of the other droughts in the other two in the 19th century as well. Now, an awful lot of what my time is spent, and that of my group, is working out what the geophysical fluid dynamics is that links together tropical Pacific sea surface temperatures with droughts in the mid-latitudes. And that gets rather technical, and I'm just going to gloss over it, but it's 90% of what we do, I think. But just to give you a taste of it, this is averaged around longitude circles, so this is latitudes from the southern hemisphere to the northern hemisphere. This is height in the atmosphere from the tropopause down to the surface. And the color is the temperature, and the contours are the zonal mean zonal winds. So you're basically looking at features like the jet stream and so on. And this is averaged over the model during the 1890s drought. When the tropical Pacific sea surface temperature is cold, it tends to make the entire tropical troposphere cold, and when that happens, the jet streams in both hemispheres migrate poleward. This is the summer season, and this is the winter season. That has an impact on the way storm systems move in the atmosphere with a